this is work that Liz and I have been working on for a good while now. And in fact, I gave a talk that's somewhat similar to this about a year ago, but we've changed the model substantially. We've more or less changed the formulation of the model, and now we're doing morphology comparisons as well as sediment transport comparisons. And since this is a small group, I sort of hope that this can be a discussion rather than a lecture. But you know, if you want to wait till the end, that's fine. Or if you want to interrupt me during the presentation, I would entertain that too. So in terms of motivation, I've used this slide before. The last time I gave this talk, I used this same slide, but I think that it is fairly motivating. So I included it once again. At the core, we're more or less wed to the phase average modeling platform. And so we're not modeling every wave. We're not modeling every crest and every trough for the real work that we're doing. We're modeling rather the statistics of the wave. So that means the mean water level and the standard deviation of the excursion, so the wave height in a statistical way. So those models would think about, you know, like AdCirc, ST wave, the union of those two in StormSim, CMS, XBeat, Seashore. These are all examples of the phased average modeling platform. And we do that for good reason. When it comes to the hydrodynamics, the solution to those equations is both stable and reasonably accurate. So, you know, Batches and Janssen now 50 years ago, 50 years ago, 45 years ago, more or less laid out the random distribution of waves and their and braking parameters throughout the surf zone. And those reached some level of accuracy. But when it comes to the sand transport problem, the accuracy lags. And we put a great deal of resources into making these estimates and making the sediment transport more reliable. And yet, several years ago, there's a publication that came out in Coastal Engineering that said that both XBeach and Seashore, which are sort of flagship process-based models, that they showed limited skill when used without calibration. And even with calibration, at the same site, they showed that they had limited skill. So we really sort of lost our way. And it turns out there's a yawning gap in the difference in what process-based solutions or models promise and what they deliver. And the question really should be, why is it that they failed to deliver on this promise? At least in part, that's due to what I would call failure in closures. So let me give you an example of what a closure is. And the one that we're working on today is, and this is an example here, but we'll be talking about this one again and again, is the cross-shore sediment transport problem. So Q over bar is the time average sediment transport. That's simple enough to write down, right? It's the product of the concentrate, the volumetric concentration and the total velocity. So that can be parsed out into the steady part, which is the first part, plus the wave-related part. And if we looked at this in its simplest form, where the concentration is just a function of the orbital velocity or the total velocity, the solution for Q, the transport, is actually fairly complicated in several ways. The first way is that the waveform for the wave orbital velocity may depart from the sinusoidal part. So that means you can have either a sawtooth wave or a skewed top to bottom wave, an asymmetric or a skewed wave. The second way that the problem is complicated is that Q isn't necessarily a linear function of U or U squared or U cubed. So that, like for instance, because you may have sediment initiation that's based on a Shields parameter, or you could have phase lags in the concentration relative to the forcing that may go like U cubed. And finally, in terms of the computational problem, when you may have wave terms that are onshore, large wave terms that are onshore, like due to the onrush under the crest, and then you have a large offshore related transport under the trough. And what you're really after is the small residual or the small difference between those two. So in terms of the physics, it's actually a fairly complicated problem. And when it comes to models like XBeats or Seashore, these phase average technologies, when you actually try and make these process-based estimates, thus far they've been based on pretty much guesses. And so the question is it hopeless? And perhaps the idea of collapsing these closures, like in the cross-shore sediment transport, to a simple algebraic expression is actually hopeless. Now, the multiscale is another option, and I'll talk about that in a second. But on the right-hand part of this panel, I'm showing you there's two experiments that I'm going to compare with today. First is called BARSED, and we'll use that to compare the sediment transport directly with. And then the next one is at Oregon State, they did something called the Great Erosion Experiment, which is a large morphological change laboratory experiment, and I'll compare the same model to both of these cases. So what are the alternatives if we're not going to just guess like Seashore does? One alternative, the one that we'll be talking about in this talk, is to utilize a finer scale model to resolve the phase-dependent quantities. And I call these simple and complex, but that's probably not the best expression. I think that the first one is simple because I understand it, and the second one is complex because I don't. But the simple one uses phased average quantities along with an empirical procedure to determine the details of wave shape, like in a phased, resolved way, and it applies the representative hydrodynamics to equations that govern the relevant processes. And the relevant processes are, of course, the sediment transport problem. The second solution or way out of this conundrum is what I call the complex one, and that's where you build a well-populated library of suitably accurate responses for use by AI or machine learning. And maybe complex isn't the right way to say it, but everyone who's honest about AI says at least it's opaque, right? It may not be complicated in its solution, but it's certainly not clear what's going on. So I'm not covering that today. I'll cover what I'm calling the simple or the process-based solution or alternative to this conundrum. Okay, so here's the new modeling strategy sort of laid out as a recipe. What we're going to do is we're going to use the numerically derived closures in the phased average system after we build them. So we deploy first the phased average model. So that could be CMS wave and CMS flow, for instance, or Batchison-Janssen or CStorm or whatever phased average model we want. From that, of course, we get statistics. We get the water depth, we get the wave heights, we get U and V as currents. We don't, of course, have the phase resolved results yet, and those are important for the sediment transport problem. So the second step is you estimate the skewness and asymmetry from the Ursel number, and you do that in a manner similar to Roosync, and that's an empirical step. You just sort of invent the information on that step. So you invent the time series of the free stream velocity. So that's the wave orbital part. In this case, we're only using the wave orbital velocity in the horizontal direction and in the direction of a cross-shore transect, because we've only applied this in a two-dimensional world so far, so vertical and cross-shore. Then we can numerically evolve the relevant physics. That could be the vegetation forces of the sediment concentration. Of course, today I'm concentrating on the sediment concentration. And then with the detailed estimates of these phase-resolved physics, we can compute what the time average is. And then we can numerically average them and incorporate these closed values back in the phased average model. So one of the steps was, you'll recall, after having what the phased average results were, that we would invent what the phase resolved results would be. So these are the BARSED experiments. So I'm using these BARSED experiments that were done a couple years ago by Ryan Mieres as a way of checking not only the wave part, but also the sediment part. So these are two cases where we have wave periods of 5, 7, and 9 seconds. And we do predictions of what the wave height is. And then from that, we estimate what the wave form is. The data is shown here, solid blue lines. And the predictions of the model with skewness and asymmetry are shown as the dashed black line. And just as a way of checking whether or not we have this wave shape right, we're looking at the extrema, so the crest and the trough values for the cross-shore wave orbital velocity. And they're shown as a 1-to-1 plot here in the right-hand panel. So you can see for the crest, we're actually doing very, very well, meaning that the predicted crest values are very similar to the measured crest values. The values for the lowest frequency wave, the 9-second waves, aren't as good in the trough as they are for the 5 and the 7-second wave. But all in all, they're probably reasonably well predicted here. So this is the empirical procedure we use to move from, we're testing here the empirical procedure that we use to move from the phased average world into the phased resolved one. And so while they're not perfect, they're probably suitably accurate for the next steps, which is to start thinking about the sediment transport problem. And there's sort of a lot tied up in this slide, and I apologize for that, but let's just split it up into two regions. The region below the boundary layer, which is shown as a dashed black line. So we have underneath that, we've got a bed load that's being transported, and that's being done directly as a function of the excess shear stress, which I'll cover here in a second. Above it, it's a little bit more complicated. We assume that we've got a vertical profile, and that vertical profile is given by an exponential function, which is equivalent to saying that at any given time, the fallout of the sand is in balance with the amount of upward diffusive sediment transport that's going on because of the concentration profile. So whether or not that's actually a good estimation of the actual sediment transport profile, I'm not totally sure. There's some evidence that that's, in terms of its shape, that on average it's okay. We're also having it change instantaneously, which I'll talk about in a second. And whether that is also reasonable or not, I'm not sure. But nevertheless, the advantage of making that prescribed profile, that prescribed exponential profile, is that we can integrate it analytically, which we're doing here on the upper left, so that we can get the volume of suspended sediment, and then the total volume of suspended sediment being transported by the velocity u is equal to the total suspended sediment transport, QS. I'll also point out here graphically, sort of more or less as a cartoon, I'm also showing with the balance, which is these terms which are in the sediment transport concentration balance, was a pickup and a fallout, P and F. So the advantage of doing this, you of course incur a little bit of error by making this assumption of what the vertical profile looks like. The advantage is substantial, though, in terms of stability and efficiency, because you've moved from what is a fully two-dimensional evolution problem in time into a one-dimensional problem that's an evolution in time. So that's substantial, and whether or not it's totally accurate, no, of course it's not totally accurate. Whether it's sufficiently accurate is really the question. Because when it comes to sediment transport, there's no end to the complexity that you can add to a model. The question is whether or not you can get away with some simplifications like this. And so far, I think that we probably can. Okay, so here's the bed load layer model that I was talking about. It's directly computed from the excess shear. It's a simple traction or energetics model that assumes the transport is in equilibrium with the forcing. And by equilibrium, I mean, as soon as the forcing changes, the bed load changes. And there's plenty of evidence that that's reasonable for the bed load. There's no lag between the amount of transport that's taking place and the forcing that's taking place. And so this is very similar to the Meyer-Peter-Muller model, where we have now an expression for the transport. And the important part of this is that you have a non-dimensional shear stress here, theta. And so, and theta critical is that initiation of transport that I was talking about. So theta less theta critical is the excess shear stress. And sometimes people call these U cubed models. And the reason is because theta goes like U squared. So U squared to the 3/2 is U cubed. So this is what they sometimes call a U cubed model. And Meyer-Peter-Muller is a famous one. The last term in this expression for the sediment transport in the boundary layer or in the bed load is G sub S, and that's due to the impact of the slope. And I've given you the expression for G sub S, which just looks complicated because I have all those sine terms in it, and it's not really very complicated if you understand generally what it does. And so now I'll show a bunch of expression or examples like this figure on the right here, where I'll show what the wave shape is and whether or not you include the effects of the bottom shear slope, the bottom slope. So you can see that the shape here is a sinusoidal curve. So it has the same peak and trough, and it has no asymmetry. So no skewness, no asymmetry. But it does include the effect of the slope, which I've shown here as a red arrow that slides or showing sand moving down. And if you look at, so this is the forcing, and there's a couple of effects you can see. First is that you've got the sediment initiation shows up as this flat region here near the zero crossings of U. But the other important thing to notice is that if you have water that's moving uphill, right in the positive phase under the crest, that you end up with an expression for the bed load transport that's reduced relative to its expression where you don't include the slope. So if you don't include the slope, it's shown as a dashed black line. But if you do include the slope, what you'll notice is there's less transport in the uphill portion phase of the wave, and an enhanced transport in the downslope part of the wave. Sorry about that. Which is, you don't need to understand all the details of this, but you get it from an intuitive sense that if you have a slope that's heading uphill like this, that you're going to have more downslope transport than upslope transport. So that's one of the things, the physical processes that's easily included in this phase resolved world that's not at all easily included in the phase average one. So that's one of the shortcomings that we can overcome relatively easily using the multi-scale modeling approach. I mentioned it earlier, but I don't want to get too caught up in the details here. But the sediment transport that's taking place in the suspended layer can be phase lagged relative to the forcing. So it's not instantaneous, which is why we need this evolution equation that's shown as the boxed equation that says that the change in the sediment, the total volume of sediment, is equal to the advective gradient, the advective part, the advective term, plus the pickup less the fallout. And the fallout's relatively easy to cast using the computed values of the volume of suspended sediment and also the prescribed vertical profile. So that's an easy expression for the pickup, the fallout. The pickup is not quite as obvious. But it's cast to have the correct units and the time steady asymptote. So this one is more or less intuitive as an expression. But the pickup now is a function, and much like the fallout, it's a function of the fall velocity and some of the details of the profile themselves, including the eddy viscosity or sediment diffusivity. Except that now we have also an expression called the VS, so the suspended sediment volume that's in equilibrium. And to cast that as something that we know, we're using a trick out of the Seashore playbook, saying that the total volume of suspended sediment in equilibrium, so that's if things were to go on forever without any time variation, that it would be a function of the dissipation due to breaking and the dissipation due to friction, which is d sub b and d sub f, along with some empirical parameters. So again, this is an expression that we're adopting because there's been some skill in predicting sediment concentrations by the Seashore family of models. So we just borrowed that part that we know to be successful. And recall that now we're going to be making all of these calculations in the phase resolved world. So we need to have a phase dependent sediment pickup. And of course, there's no first principle statement for that. You'll recall that we have, these are the expressions I gave in the last slide. We're going to need to figure out a way of making these things time dependent, because when it comes to the equilibrium values, those are phase dependent values. The frictional dissipation is relatively easy to express. We know what U is. U is invented by our time series, our synthetic time series. So we can figure out what the dissipation due to bottom friction is because we have values for U. There's no analogous accepted model existent for the breaking part of it. So we've adopted a more or less intuition base. We know what it is in the phased average world, right? Because Batches and Janssen is one solution to that problem, right? We know what the phased averaged bottom breaking dissipation is in that. So what about if we say that it's not equal to that value throughout the entirety of the phase, but it's distributed out throughout part of it? And that's what this expression says here, that the dissipation due to breaking with a tilde, meaning it's phase resolved, is equal to some scalar coefficient to make it have the right value, and then Heaviside functions, where the Heaviside function for eta is for all eta greater than the mean eta, and the Heaviside function that's a function of the slope of that. And in that case, we have a Heaviside function is equal to 1 for all rising values for eta. So for all values of eta that are larger than eta bar, and for all rising values, meaning for this region here, throughout that region of the phase, that's where we assume that we have the dissipation due to breaking. So the dissipation due to breaking from our phased average world is shown here as about a 0.1. If we redistribute that throughout the phase such that it happens for all values where eta is greater than eta bar and d eta dt is greater than 0, then you end up with a time-dependent value for the dissipation due to breaking that's shown as a dashed red line. Now again, is this exactly correct? Probably not. But you need to have some way of moving from the phased average world into the phased resolved world without a great deal of numerical complexity. So it's a pragmatic solution to the problem. Finally, the last missing piece of this puzzle is that we need sediment diffusivity, which plays a role in the way sand is being transported vertically, and we've opted for something that's similar to what Svensson did a good while ago, and we have a diffusive mixing coefficient for the sediment that's equal to the eddy diffusivity or turbulent diffusivity. We assume those two are equal, and it derives from a addition of three values. One's due to the waves, one's due to bottom shear dissipation and one's due to breaking dissipation. And those have three coefficients, three different, so those make up the length scales. The length scales are the cube roots of the diffusivity or diffusion parts or dissipation parts. And then you need a length scale. So the first is the boundary layer. This is the length scale for the part that derives from the bottom shear dissipation. The total depth is the length scale that derives from the breaking dissipation. And then you've got three empirical coefficients. Now, there aren't really published values for these coefficients, so we're more or less using these as free parameters in this model. Although there's, in the case of the breaking dissipation, there are some data that are available, published, not calculated and published. So we do try and use those. But this is all in lieu of having a proper turbulence model. And the ramifications of using this instantaneous transport of turbulence and sediment is not really totally clear yet. But as soon as a wave breaks, it has sand that's being transported instantaneously higher in the water column. Not a lot of it, but some of it. So that's, from an intuitive standpoint, that's not very satisfying. Whether it actually becomes a material problem, that's not clear yet. Okay, so let's just talk about some simple examples of how this model behaves in more or less idealized forcing conditions. We have a flat section and a planar beach. We're going to walk through simple cases where you have a slightly elevated water height on one case relative to another. So, wave height. You have a wave height that's about 1 meter and then 1.4 meters. So a low and a high, although they're not that different. Not that one's really low and one's really high, but rather I wanted to show you how the variation in wave height results in variations in the sediment transport problem. We're going to use this idealized bathy that I just talked about, a time period of 8 seconds, these slightly increasing wave height, and just more or less for demonstration purposes, I'm using a 3.5 millimeter grain size. These results, which I'm showing you here, which are the phased average results, they're consistent with Batches and Janssen 78. So I'm not even going to show them to you here. There's nothing new about them. And we're going to look at the impact of wave shape, bed slope, and undertow, so the current part of the problem, in using this simple example. So again, I have this cartoon here where it demonstrates the three impacts that we're going to be investigating. First is the shape. So we're looking at a sinusoidal wave. I'm not including the slope because there's no arrow here, and I'm not including undertow because there's no arrow here. So the wave shape is linear, the slope effect is off, and the undertow is off. So you end up with a bed load that doesn't depend on slope, and it has a linear wave shape. So it's not that you have zero bed load, it's that you have a positive bed load that's equal to a negative bed load. So on average, the bed load's about 0. When it comes to the suspended part, you still have an onshore directed sediment transport owing to the phasing of that dissipation problem, right? Remember the breaking dissipation that we artificially distributed throughout the phase. So just due to the phasing of that problem, you end up with a suspended sediment transport that's onshore completely in this case. So this is the low wave case, and this is the high wave case. Now we turn to having a linear wave shape, a bottom slope that is turned on, the impact of the bottom, the bed slope is turned on, and the undertow is turned off. So you get a suspended load that's actually very similar to what you got before. You're still getting an onshore transport of the suspended load, and that's really should be obvious in hindsight, because the bed slope doesn't play any role in how we're computing the suspended part of the transport. In reality, it should play some role in the initiation of sediment transport, because you have a slightly greater likelihood of moving sand downslope rather than up if initiation is taken into effect, if the impact is included, but we haven't done that in this model. And then you see that because of the impact of the slope, even though it's a linear wave shape, right? There's no skewness or asymmetry to the forcing function. You end up with a bed slope effect that drives the sand offshore. Shown here is these two blue lines. Negative meaning offshore. Okay, now let's include a nonlinear or sort of a natural wave shape, and not this. We won't include the impact of the slope or the undertow again. The wave shape being skewed and asymmetric ends up driving both the bed load and the suspended load onshore. So that squares with what our intuition should say. But of course, it's not reasonable to take any of these in isolation, but it's informative anyway to show you how this model behaves. So now if we use the linear wave shape, we don't include the slope, but we include the current part of this problem. The first thing you'll notice is that the otherwise onshore suspended sediment transport is greatly reduced or greatly attenuated, although it's still onshore directed. And then there's a dramatic effect in terms of the bed load, which ends up being strongly directed offshore due to the undertow effect. So now if we could include all the effects, which is sort of like the natural case we would want, we would want the nonlinear wave shape or the natural wave shape. We want to include the bed slope and we want to include the bed load. Then we get this more or less complex conglomerate of all these effects. You get a suspended transport that's onshore and a bed load that's both onshore and offshore. Now, this need not even correspond very well to a natural beach, right? Because this is all sort of invented in terms of its slope. But it's more or less designed to illustrate what the impacts of these different effects are that are all included in this phase resolved model. The last thing I want to talk about is that there's an impact of sediment grain size. So if we now include a small grain size with a grain size of, gosh, I wish I had written here what it was. I don't think I have. Sorry about that. All I have written is the fine sand and the coarse sand. I'll fix that. But what you find is that that for your coarse sand, which is shown as the coarse lines, and you get a substantially different transport picture in the suspended problem than you do in the fine sand. In the bed load problem, the coarse and the fine sand grains lie directly on top of each other. They're not a function of sand size in any way. And you'll notice that if you look back at the Meyer-Peter-Muller expression, it's that you have sand transport that's being driven by excess shear and not by any formula that depends on your grain size in any way. Of course, your sediment problem for the suspended is substantially different. You get a coarse grain size that's directed onshore and an erosional one that's offshore. And it's interesting to think about that in terms of the Dean number, which is one of the ways that people sometimes use to separate onshore and offshore directed sand transport, where it's generally thought that if you have a Dean number that's larger than 2, that you have an erosive profile. And in this case, what we have is a Dean number for the coarse sand that's about 2.6. So it's not exactly 2, but the trend is right, correct? That you have a Dean number for the fine sand that's equal to 8, and so that would be clearly erosive. And what you see here is another demonstration where you have a clearly erosive case with the fine sand. And so what we're doing here is trying to develop a system where we're not trying to guess anymore what the impact of a fine or coarse grain size is, that we rather compute it. And so these first order processes of shape and slope and undertow and grain size, they're now being computed rather than being just guessed as they do in some of the sediment transport models that we now use. Okay, so when it comes now to actual comparison to actual data, let's return to the bar set experiment, which we first used to compare our velocity profiles. And what I've shown here is transport that goes on in the suspended load, which are red dots, and in the bed load, which are blue dots. And under the crest, so if you integrate the total amount of sand that's being transported under the entirety of the crest or under the entirety of the trough for the free stream part of the velocity, and you compute that and compare it to the data, you get this 1-to-1 plot that I'm showing here with 20% error shown as the dashed black lines. So I'm fairly happy with this, and this is a way of determining whether or not we're doing the phase resolved gross transport accurately. I'll point out that the coefficients that go into the sediment diffusivity are being tailored to match these data. Well, these data and the time averaged one. And also point out that, so skewness plays a role here, both in the bed load and in the suspended load. The bed load, of course, because it goes like the SS shear, and the dissipation is a function also of the skewness. And so those are included in sort of an inherent way in these model results. But the asymmetry, the sawtooth part of the profile, is not included. So if that plays a role due to pressure gradients or whatever else, boundary layer thinning or some of the other possibilities, that's not included in this. I'm not saying they're not important. I'm just saying they're not included here. And of course, we're not after the phase resolved results. We're after the phased averaged ones. And if you then numerically average them and compare them to the measurements, you get the following figure, which isn't nearly as impressive. At least things are mostly in the right quadrant in terms of data and model as a comparison. It's really, really difficult to make that prediction from the last step to this one. The average transport's an order of magnitude smaller than the gross transport. And I think that, again, the bed load are shown as the blue values, and I think that they're probably suitably accurate. There is some significant error in the suspended transport, and I think, or we think, that probably derives from errors in the undertow, so that the values of the time steady currents for these short packets of waves are probably dissimilar from the time steady undertow values that you get from linear wave theory. So one of the things we've been meaning to do, and we're going to probably do in the next set of data, is to not make predictions on some of these values. At this point, we're making predictions on all the U and U bar values. So that's the wave orbital velocities and the time average of the wave orbital velocities. And in the next round, we may try to just put in the measured values for the velocities and see if we can do the sediment transport problem a little bit more accurately. Now, moving on to morphology and using the same values of the empirical parameters that we talked about in the sediment transport problem, we'll turn to a long run of erosive waves that were done at the Oregon State University in their super tank a couple of years ago. And this is a signal that has, a strong signal. So I'm still using it now as a way of doing first order checks on our models. And when it comes to toggling the things that we were talking about in the last 10 slides, it turns out that the slope effect is the one that plays the largest role in the prediction problem here. And when it comes to time evolution, you'll see that I have several colors, starting with purple and ending with, I guess, purple, unfortunately. And the data are shown as solid lines, and the dashed lines show what is predicted by the model. So right off the bat, you'll note that when it starts at time from 0 to the first hour, that you end up with an under prediction of the sediment transport morphology and associated morphology. However, at the end of that 10 hours of erosive wave conditions, you end up with an over prediction of the morphology change. And to tell you the truth, I've been struggling with this for a couple of days when I was working on it. Really struggling to understand why that would ever be. I think that it probably derives not so much from a problem with the sediment transport problem as it derives from a problem with not including something like infragravity waves, which can be substantially significant and dominating in these really shallow regions where you have this weird shelf berm that's being developed here. That there may be the infragravity waves in these regions that are happening hydrodynamically that I'm not including at all, which is another reason why, if I had more detailed data for this experiment or any experiment, I could include those measured hydrodynamics in waves rather than predicted ones. But again, if anyone has any ideas about why I would initially see an under prediction of the morphology change and then finally an over prediction of the morphology change, I'd be interested to know what people think. Okay, and so now we're moving on to the next set of experiments that Liz and I are going to be looking at, and this all derives from the US CRP SED collab, which in 2025 had a series of scholars and university professors come and conduct experiments at CHL and the CHL wave flume. I'm really looking forward to this. The one that I'm thinking about starting with, and Liz and I have been meeting with this group regularly now, is headed up by the University of Washington and Oregon State. And they call their experiment STONE, which stands for Sediment Transport Collaborative Laboratory Experiment. And they have and I'll show you the setup here in a second, but they have repeatable focused wave packets. So this is another case where we have a small section of sand in an otherwise hardened off flume bed, where they're going to be using small wave packets and doing detailed measurements of the hydrodynamics, waves, and sediment transport. One of the interesting things about this next set of experiments that I'll be able to make use of is that they're actually going to be using smooth particle hydrodynamics models as a wave and hydrodigital twin of the experiment. So that means that if they do a sufficiently good job at predicting what the waves and currents are throughout at where they're measuring it, I can assume that wherever they're not measuring it is also being reasonably well predicted. So when it comes to sparsity of data, which sometimes bites us when we're using laboratory experiment data, we'll be able to make use of these digital twin data. Okay, so here's the setup. This is again a digital flume. A one-dimensional flume. And this part of it's more or less a conventional data collection. It's hard bottom except for this sand pit here. You've got a free surface that's being measured both with LiDAR and with these capacitance or surface piercing wave gauges. And then you get U and V and W, so the three components of velocity from the ADVs. That's more or less conventional. What's not conventional is their additional collection that goes on for the sediment transport. And so what they're using for the sediment transport is an acoustic instrument that measures two things, right? It measures both the velocity through Doppler shift, and then it measures the levels of backscatter that it sees at the same time. And from that, you can induce, with calibration, you can induce what the concentrations are. So we not only get velocities in U and V and W, we also get the concentration. So we're getting transport, right? And when it comes to comparison of data to models, the concentration is great and the velocities are great, but actually getting the transport is key. And some of the transport expressions, the values that I'm showing previously, are based on co-located different sorts of instruments where there was always issues, and there always will be issues when you have two instruments, one's measuring concentration, one's measuring velocity. They're not exactly co-located. So when it comes to rapidly varying time and space problems, that ends up being an issue, which I hope that we won't have nearly as much trouble with in this case. Okay, so I think I'm in time here. Yeah, I'm doing all right. So I talked about a multi-scale approach, which I think which affords us the opportunity to incorporate some of the first-order phase-dependent processes that are being missed in phased average models now. You have a problem that's being dominated by the waves, and they don't even compute what the wave crest and trough is. So it's not really all that surprising that these first-order phase-dependent processes are being missed, and we're not doing a very satisfactory job in terms of skill. So it includes, now if we use a multi-scale approach, it relatively easily includes the impact of bed slope, the wave nonlinearity, so the skewness and asymmetry. We can fully resolve the bottom shear stress due to waves and currents. And then if you make a set of assumptions, which we did, you can make estimates of what your coupled phase coupled variation in velocity and concentration are. So it's the simple two-scale approach that we presented. I call it simple, but maybe other people don't see it that way, where we move from the phased average world into these idealized phase resolve world. If you do this, then you can make process-based estimates of the wave-related physics. So you can include the shape of the waveform, and you can include the slope, the currents, the grain size. All these things are included without guessing what the coefficient, the parameters are. I think that the gross transport, that's under the crest and the trough, that are predicted reasonably well with compared to data. Net transport aren't so great. And again, I think that may derive from the fact that we're not predicting what our currents are very well. And you can imagine that there is small residual in the cross-shore problem between the onshore and the offshore transport is dominated, at least in part, by that current part. So we really owe it to the community to sneak in and use measured values for those for those currents rather than predicted ones. The morphology change is a little bit confusing to me. It's underpredicted initially and then overpredicted. So I think this probably indicates a shortcoming in the simple description. And that simple description problem can be either in the waves, in the way the waves are being broken, or the, so it can be in the statistical part of it, the eta, the free surface prediction part of it, or it can be in the sediment transport part of it. And that's not totally clear to me yet. And we're looking forward to this new effort with UW and OSU. We think that the data that they've collected already, although it's not been analyzed yet, is ideal for comparison with this model. And it's ideal from their perspective too, apparently, because they're not also comparing a sediment transport model to it. So they're interested to see these data being used in that capacity. And we expect that it'll be several months before their data are ready. They've already started working on the analysis and QA/QC of those data, and they've been in touch with us. But we expect that our first results of this model and the model to data comparison will be ready by March.